Chapter 7 of Is Mars Habitable? This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Is Mars Habitable? By Alfred Russel Wallace. Chapter 7. A suggestion as to the canals of Mars. The special characteristics of the numerous lines which intersect the whole of the equatorial and temperate regions of Mars are their straightness combined with their enormous length. It is this which has led Mr. Lowell to term them non-natural features. Schiaparelli in his earlier drawings showed them curved and of comparatively great width. Later he found them to be straight, fine lines when seen under the best conditions, but as Mr. Lowell has always seen them in the pure atmosphere of his observatory, both of these observers were at first doubtful of their reality, but persistent observation continued at many successive oppositions compelled acceptance of them as actual features of the planet's disk. So many other observers have now seen them that the objection of their unreality seems no longer valid. Mr. Lowell urges, however, that their perfect straightness and their extreme tenuity of their uniformity throughout their whole length, the dual character of many of them, their relation to the oases, and the form and position of these round black spots, are all proofs of artificiality and are suggestive of design, and considering that some of them are actually as long as from Boston to San Francisco, and relatively to their globe as long as from London to Bombay, his objection that no natural phenomena within our knowledge show such regularity on such a scale seems at first a mighty one. It is certainly true that we can point to nothing exactly like them either on the earth or on the moon, and that these are the only two planetary bodies we are in a position to compare with Mars. Yet even these do, I think, afford us some hints toward the interpretation of the mysterious lines. But as our knowledge of the internal structure and past history even of our Earth is still imperfect, that of the Moon only conjectural, and that of Mars a perfect blank, it is not perhaps surprising that the surface features of the latter do not correspond with those of either of the others. Mr. Pickering's suggestion. The best clue to a natural interpretation of the strange features of the surface of Mars is that suggested by the American astronomer Mr. W. H. Pickering in Popular Astronomy, 1904. Briefly, it is that both the canals of Mars and the rifts, as well as the luminous streaks on the Moon, are cracks in the volcanic crust caused by internal stresses due to the action of the heated interior. These cracks he considers to be symmetrically arranged with regard to small craterlets, Mr. Lowell's oases, because they have originated from them just as the white streaks on the Moon radiate from the larger craters as centers. He further supposes that water and carbon dioxide issue from the interior into these fissures and, in conjunction with sunlight, promote the growth of vegetation. Owing to a very rare atmosphere, the vapors he thinks would not ascend, but would roll down the outsides of the craterlets and along the borders of the canals, thus irrigating the immediate vicinity and serving to promote the growth of some form of vegetation which renders the canals and oases visible. See footnote 13. This opinion is especially important because next to Mr. Lowell, Mr. Pickering is perhaps the astronomer who has given the most attention to Mars during the last 15 years. He was for some time at Flagstaff with Mr. Lowell, and it was he who discovered the oases or craterlets, and who originated the idea that we did not see the canals themselves, but only the vegetable growth on their borders. He has also observed Mars in the southern hemisphere at Arequipa, and he has since made an elaborate study of the Moon by means of a specially constructed telescope of 135 feet focal length, which produced a direct image on photographic plates nearly 16 inches in diameter. See footnote 14. It is clear, therefore, that Mr. Lowell's views as to the artificial nature of the canals are not accepted by an astronomer of equal knowledge and still wider experience. Yet, Professor Pickering's alternative view is more a suggestion than an explanation, because there is no attempt to account for the enormous length and the perfect straightness of the lines on Mars, so different from anything that is found either on our Earth or on the Moon. There must be evidently some great peculiarity of structure or of conditions on Mars to account for these features, and I shall now attempt to point out what this peculiarity is and how it may have arisen. The meteoric hypothesis. During the last quarter of a century, a considerable change has come over the opinions of astronomers as regards to the probable origin of the solar system. The large amount of knowledge of the stellar universe, and especially of nebula, of comets and meteor streams, which we now possess, together with many other phenomena, such as the constitution of Saturn's rings, with the great number and extent of the minor planets, and generally of the vast amount of matter in the form of meteor rings and meteoric dust in and around our system, have all pointed to a different origin for the planets and their satellites than that formulated by Laplace as the nebular hypothesis. It is now seen more clearly than at any earlier period that most of the planets possess special characteristics which distinguish them one from another, and that such an origin as Laplace suggested, the slow cooling and contraction of one vast sun-mist or nebula, besides presenting inherent difficulties, many think of them impossibilities, in itself does not afford an adequate explanation of these peculiarities. Hence has arisen what is termed the meteoric theory, which has been ably advocated for many years by Sir Norman Lockyer, and with some important modifications is now becoming widely accepted. Briefly, this theory is that the planets have been formed by the slow aggregation of solid particles around centers of greatest condensation. But as many of my readers may altogether be unacquainted with it, I will here give a very clear statement of what is from Professor J. W. Gregory's presidential address to the geological section of the British Association of the present year. He began by saying that these modern views were far more practical to use of men of science than that of Laplace, and that they give us a history of the world consistent with the actual records of geology. He then continues, according to Sir Norman Lockyer's meteoric hypothesis, nebulae, comets, and many so-called stars consist of swarms of meteorites, which, though normally cold and dark, are heated by repeated collisions, and become so luminous they may even be volatilized into glowing meteoric vapor. But in time this heat is dissipated, and the force of gravity condenses a meteoric swarm into a single globe. Some of the swarms are, says Lockyer, truly members of the solar system, and some of these travel round the sun in nearly circular orbits like planets. They may be regarded as infinitesimal planets, and so Chamberlain calls them planetesimals. The planetesimal theory is a development of the meteoric theory, and presents it in an especially attractive guise. It regards meteorites as very sparsely distributed through space, and gravity as powerless to collect them into dense groups, so it assigns the parentage of the solar system to a spiral nebula composed of planetesimals, and the planets as formed from knots in the nebula, where many planetesimals had been concentrated near the intersection of their orbits. These groups of meteorites, already dense as a swarm of bees, were then packed closer by the influence of gravity, and the contracting mass was heated by the pressure even above the normal melting point of the material, which was kept rigid by the weight of the overlying layers. Now, adopting this theory as the last word of science upon the subject of the origin of planets, we see that it affords immense scope for diversity in results depending on the total amount of matter available within the range of attraction of an incipient planetary mass, and the rates at which this matter becomes available. By a special combination of these two quantities, which have almost certainly been different for each planet, I think we may be able to throw some light upon the structure and the physical features of Mars. The probable mode of origin for Mars. This planet, lying between two of much greater mass, has evidently had less material from which to be formed by aggregation. And if we assume, as in the absence of evidence to the contrary we have a right to do, that its beginnings were not much later or earlier than those of the Earth, then its smaller size shows that it has in all probability aggregated very much more slowly. But the internal heat acquired by a planet while forming in this matter will depend upon the rate at which it aggregates and the velocity with which the planetesimals fall into it. And this velocity will increase with its mass and consequent forces of gravity. In the early stages of a planet's growth, it will probably remain cold, and the small amount of heat produced by each impact being lost by radiation before the next one occurs. And with a small and slowly aggregating planet, this condition will prevail till it approaches its full size. Then only will its gravitative force be sufficient to cause incoming matter to fall upon it with so powerful an impact as to produce intense heat. Further, the compressive force of a small planet will be a less effective heat-producing agency than in the case of a larger one. The Earth, we know, has acquired a large amount of internal heat, probably sufficient to liquefy its whole interior. But Mars has only 1/9 part the mass of the Earth, and it is quite possible and even probable that its comparatively small attractive force would never have liquefied or even permanently heated the more central portions of its mass. This being admitted, I suggest the following course of events as being quite possible, and not even improbable in the case of this planet. During the whole of its early growth, and till it acquired nearly its present diameter, its rate of aggregation was so slow that the planetesimals falling upon it, though they might have been heated and even partially liquefied by the impact, were never in any such quantity as to produce any considerable heating effect on the whole mass, and each local rise of temperature was soon lost by radiation. The planet thus grew as a solid and cold mass, compacted together by the impact of the incoming matter as well as by its slowly increasing gravitative force. But when it had attained to within perhaps 100, perhaps 50 miles or less of its present diameter, a great change occurred in the opportunity for further growth. Some large and dense swarm of meteorites, perhaps containing a number of bodies of the size of the asteroids, came within the range of the sun's attraction and were drawn by it into an orbit which crossed that of Mars at such a small angle that the planet was able at each revolution to capture a considerable number of them. The result might then be that, as in the case of the Earth, the continuous inpour of the fresh matter first heated and later on liquefied the greater part of it, as well perhaps as a thin layer of the planet's original surface, so that when in due course the whole of the meteor swarm had been captured, Mars had acquired its present mass, but would consist of an intensely heated and either liquid or plastic thin outer shell resting upon a cold and solid interior. The size and position of the two recently discovered satellites of Mars, which are believed to be not more than 10 miles in diameter, the more remote revolving around its primary very little slower than the planet rotates, while the nearer one, which is considerably less distant from the planet's surface than its own antipodes and revolves around it more than 3 times during the Martian day, may perhaps be looked upon as the remnants of the great meteor swarm which completed the Martian development, and which are perhaps themselves destined at some distant period to fall into the planet. Should future astronomers witness the phenomenon, the effect produced upon its surface would be full of instruction. As the result of such an origin as that suggested, Mars would possess a structure which, in the essential feature of heat distribution, would be the very opposite of that which is believed to characterize the Earth. Yet it might have been produced by a very slight modification of the same process. This peculiar heat distribution, together with a much smaller mass and gravitative force, would lead to a very different development of the surface in an altogether diverse geological history from ours, which has throughout been profoundly influenced by its heated interior, its vast supply of water, and the continuous physical and chemical reactions between the interior and the crust. These reactions have in our case been of substantially the same nature and very nearly of the same degree of intensity throughout the whole vast eons of geological time, and they have resulted in a wonderfully complex succession of rock formations, volcanic, plutonic, and sedimentary, more or less intermingled throughout the whole series, here remaining horizontal as when first deposited, there upheaved or depressed, fractured or crushed, inclined or contorted, denuded by rain and rivers with the assistance of heat and cold, of frost and ice, in an unceasing series of changes, so that however varied the surface may be, with hill and dale, plains and uplands, mountain ranges and deep intervening valleys, these are as nothing to the diversities of the interior structure, as exhibited in the sides of every alpine valley or precipitous escarpment, and made known to us by the work of the miner and the well-borer in every part of the world. Structural straight lines on the Earth. The great characteristic of the Earth, both on its surface and in its interior, is thus seen to be extreme diversity both of form and structure, and this is further intensified by the very texture, constitution, hardness, and density of the various rocks and debris of which it is composed. It is therefore not surprising that with such a complex outer crust we should nowhere find examples of these geometrical forms in almost world-wide straight lines that give us such remarkable and, as Mr. Lowell maintains, non-natural character of the surface of Mars, but which, as seems to be, of themselves afford prima facie evidence of a corresponding simplicity and uniformity in its internal structure. Yet we are not ourselves by any means devoid of straight lines structurally produced, in spite of every obstacle to diversity of form and texture, of softness and hardness, of lamination or crystallization, which are adverse to such developments. Examples of these are the numerous faults which occur in the harder rocks and which often extend for great distances in almost perfect straight lines. In our own country we have the Tyneside and Craven faults in the north of England, which are 30 miles long and often 20 yards wide. But even more striking is the great Cleveland Dyke, a wall of volcanic rock dipping slightly towards the south, but sometimes being almost vertical, and stretching across the country over hill and dale in almost perfect straight lines from a point on the coast 10 miles north of Scarborough, in a west by north direction, passing about 2 miles south of Stockton, and terminating about 6 miles north by east of Barnard Castle, a distance of very nearly 60 miles. The great fault between the highlands and the lowlands of Scotland extends across the country from Stonehaven to near Helensburgh, a distance of 120 miles, and there are very many more of less importance. Much more extensive are some of the great continental dislocations, and often forming valleys of considerable width and length. The Upper Rhine flows in one of these great valleys of subsidence for about 180 miles, from Mühlhausen to Frankfurt, in a generally straight line, though modified by denudation. Vaster still is the valley of the Jordan, to the Sea of Galilee, to the Dead Sea, continued by way of the Wadi Araba to the Gulf of Aqaba, believed to form one vast geological depression or fracture extending in a straight line for 400 miles. Thousands of such faults, dikes, or depressions exist in every part of the world, all believed to be due to the gradual shrinking of the heated interior to which the solid crust has to accommodate itself, and they are especially interesting and instructive for our present purposes as showing the tendency of such fractures of solid rock material to extend to great lengths in straight lines, notwithstanding the extreme irregularity both of the surface contour as well as in the internal structures of the varied deposits and formations through which they pass. Probable origin of the surface features of Mars. Returning now to Mars, let us consider the probable course of events from the point at which we left it. The heat produced by impact and condensation would be likely to release gases which had been in combination with some of the solid matter, or perhaps been itself in a solid state due to the intense cold, and these, escaping outwards to the surface, would produce on a small scale a certain amount of upheaval and volcanic disturbance, as in an outer crust rapidly formed. A number of vents might remain as craters or craterlets in a moderate state of activity. Owing to the comparatively small force of gravity, the outer crust would become scoriaceous and more or less permeated by the gases, which would continue to escape through it, and this would facilitate the cooling of the whole of the heated outer crust and allow it to become rather densely compacted. When the greater portion of the gases had thus escaped into the outer surface and assisted to form a scanty atmosphere such as now exists, there would be no more internal disturbance, and a cooling of the heated outer coating would steadily progress, resulting at last in a slightly heated and later in a cold layer of moderate thickness and great general uniformity. Owing to the absence of rain and rivers, denudation such as we experience would be unknown, though the superficial scoriaceous crust might be partially broken up by expansion and contraction and suffer a certain amount of atmospheric erosion. The final result of this mode of aggregation would be that the planet would consist of an outer layer of moderate thickness as compared with the central mass, which the outer layer would have cooled from a highly heated state to a temperature considerably below the freezing point, and this would have all the time been contracting upon a previously cold and therefore non-contracting nucleus. The result would be that very early in the process great superficial tensions would be produced, which would only be relieved by cracks or fissures, which would initiate at points of weakness, probably at the craterlets already referred to, from which they would radiate in several directions. Each crack thus formed near the surface would, as cooling progressed, develop in length and depth, and owing to the general uniformity of the material, and possibly some amount of crystalline structure, due to slow and continuous cooling down to a very low temperature, the cracks would tend to run on in straight lines and to extend vertically downwards, which two circumstances would necessarily result in their forming portions of great circles on the planet's surface. The two great facts which Mr. Lowell appeals to as being especially non-natural. Symmetry of basaltic columns. We have, however, one quite natural fact on our Earth which serves to illustrate one of these two features, the direction of the downward fissure. This is the comparatively common phenomena of basaltic commons and in the giants' causeways. The wonderful regularity of these, and especially the not unfrequent upright pillars in serried ranks, as in the Palisades of the Hudson River, must have always impressed observers with their appearance of artificiality. Yet they are undoubtedly the result of very slow cooling and contraction of melted rocks under compression by strata below and above them, so that when once solidified, the mass was held in position, and the tension produced by the contraction could only be relieved by numerous very small cracks at short distances from each other in every direction, resulting in 5, 6, or 7-sided polygons, with sides only a few inches long. This contraction began, of course, at the coolest surface, generally the upper one, and observation of these columns in various positions has established the rule that the direction lengthways is always at right angles to the cooling surface, and thus whenever the surface was horizontal, the columns became almost exactly vertical. How this applies to Mars. One of the features of the surface of Mars that Mr. Lowell describes with much confidence is that it is wonderfully uniform and level, which of course it would be if it had once been in liquid or plastic state, and not much disturbed since by volcanic or other internal movements. The result would be that cracks formed by the contraction of the hardened outer crust would be vertical, and in a generally uniform material at a very uniform temperature, these cracks would continue almost indefinitely in straight line, the hardened and contracting surface being free to move laterally on account of there being a more heated and plastic layer below it. The cracks once initiated above were continually widened at the surface as they penetrated deeper and deeper into the slightly heated substratum. Now, as basalt begins to soften at about 1400 degrees Fahrenheit, and the surface of Mars has cooled to at least the freezing point, perhaps very much below it, the contraction would be so great that if the fissures produced were 500 miles apart, they might be 3 miles wide at the surface, and if only 100 miles apart, then about 2/3 of a mile wide. See footnote 15. But as the production of the fissures might have occupied perhaps millions of years, a considerable amount of atmospheric denudation would result, however slowly it acted. The expansion and contraction would wear away the edges and the sides of the fissures, fill up many of them with the debris, and widen them at the surfaces to perhaps double their original size. See footnote 16. Suggested explanation of the oases. The numerous round dots seen upon the canals, and especially at points from which several canals radiate and where they intersect, termed oases by Mr. Lowell and craterlets by Mr. Pickering, may be explained in two ways. Those from which several canals radiate may be true craters from which the gases imprisoned in the heated surface layers have gradually escaped. They would be situated at points of weakness in the crust and become centers from which cracks would start during contraction. Those dots which occur at the crossing of two straight canals or cracks may have originated from the fact that at such intersections there would be 4 sharply projecting angles, which, being exposed to the influence of alternate heat and cold during day and night on the two opposite surfaces, would inevitably in time become fractured and crumbled away, resulting in the formation of a roughly circular chasm, which would become partly filled up by the debris. Those formed by cracks radiating from craterlets would also be subject to the same process of rounding off to an even greater extent, and thus would be produced the oases of various sizes up to 50 miles or more in diameter, recorded by Mr. Lowell and other observers. Probable function of the great fissures. Mr. Pickering, as we have seen, supposes that these fissures give out the gases which, overflowing on each side, favor the growth of the supposed vegetation which renders the course of the canals visible. And this no doubt may have been the case during remote periods when these cracks gave access to the heated portions of the surface layer. But it seems more probable that Mars has now cooled down to the almost uniform mean temperature it derives from solar heat, and that the fissures, now for the most part broad shallow valleys, serve merely as channels along which the liquids and heavy gases derived from the melting of the polar snows naturally flow, and owing to their nearly level surfaces, overflow to a certain distance on each side of them. Suggested origin of the blue patches. These heavy gases, mainly perhaps, as has often been suggested, carbon dioxide, would, when in large quantity and of considerable depth, reflect a good deal of light, and being almost inevitably dust-laden, might produce that blue tinge adjacent to the melting snow caps, which Mr. Lowell has erroneously assumed to be itself a proof of the presence of liquid water. Just as the blue of our sky is undoubtedly due to the reflection from the ultra-minute dust particles in our higher atmosphere, similar particles brought down by the snow from the higher Martian atmosphere might produce the blue tinge in the great volumes of heavy gas produced by its evaporation or liquefaction. It may be noted that Mr. Lowell objects to the carbon dioxide theory of the formation of the snowcaps, that this gas at low pressure does not liquefy, but passes at once from the solid to the gaseous state, and that only water remains liquid sufficiently long to produce the blue color which plays so large a part in his argument for the mild climate essential for an inhabited planet. But this argument, as I have already shown, is valueless, for only very deep water can possibly show a blue color by reflected light, while a dust-laden atmosphere, especially with a layer of very dense gas at the bottom of it, as would be the case with the newly evaporated carbon dioxide from the diminishing snow cap, would provide the very conditions likely to produce this blue tinge of color. It may be considered a support to this view that carbonic acid gas becomes a liquid at minus 140 degrees Fahrenheit and solid at minus 162 degrees Fahrenheit, temperatures far higher than we should expect to prevail in the polar and north temperate regions of Mars during a considerable part of the year, but such as might be reached there during the summer solstice, when the snow so rapidly disappeared to be reformed a few months later. The double canals. The curious phenomena of the double canals are undoubtedly the most difficult to explain satisfactorily on any theory which has yet been suggested. They vary in distance apart from about 100 to 400 miles, and in many cases they appear perfectly parallel, and Mr. Lowell gives us the impression that they are almost always so. But his maps show, in some cases, decided differences of width at the two extremities, indicating considerable want of parallelism. A few of the curved canals are also double. There is one drawing in Mr. Lowell's book, on page 219, of the mouths or starting points of the Euphrates and Pison, two widely separated double canals diverging at an angle of about 40 degrees from the same two oases, so that the two inner canals cross each other. Now this suggests two bands of weakness in the planet's crust radiating probably from within the dark tract called the Mare Incarium, and that some widespread volcanic outbursts initiated diverging cracks on either side of these bands. Something of this kind may have been the cause of most of the double canals, or they may have been started from two or more craterlets not far apart, the direction being at first decided by some local peculiarity of structure, and where begun continuing in straight lines owing to the homogeneity or uniform density of the material. This is very vague, but the phenomena are so remarkable and so imperfectly known at present that nothing but suggestion can be attempted. Concluding remarks on the canals. In this somewhat detailed exposition of a possible, and I hope a probable, explanation of the surface features of Mars, I have endeavored to be guided by known facts or accepted theories, both astronomical and geological. I think I may claim to have shown that there are some analogous features of terrestrial rock structure to serve as guides towards a natural and intelligible explanation of the strange geometric markings discovered during the last 30 years, and which have raised this planet from comparative obscurity into a position of the very first rank both in astronomical and popular interest. This widespread interest is very largely due to Mr. Lowell's devotion to its study, both in seeking out so admirable a position as regards altitude and climate, and in establishing there a first-class observatory, and also in bringing his discoveries before the public in connection with a theory so startling as to compel attention. I venture to think that his merit as one of our first astronomical observers will in no way be diminished by the rejection of his theory, and the substitution of one or more in accordance with the actually observed facts. Footnote 13. Nature, Volume 70, page 536. Footnote 14. Nature, Volume 70, May 5th, page 11, supplement. Footnote 15. The coefficient of contraction of basalt is 6 times 10 to the minus 6th for each 1 degree Fahrenheit, which would lead to the results given here. Footnote 16. Mr. W. H. Pickering observed clouds on Mars 15 miles high. These are projections seen on the terminator when the planet is partially illuminated. They were at first thought to be mountains, but during the opposition of 1894, more than 400 of them were seen at Flagstaff during 9 months' observation. Usually they are a rare occurrence. They are seen to change in form and position from day to day, and Mr. Lowell is strongly of the opinion that they are dust storms, not what we term clouds. They were mostly about 13 miles high, indicating considerable aerial disturbances on the planet, and therefore capable of producing proportional surface denudation. Appendix. A suggested experiment to illustrate the canals of Mars. If my explanation of the canals should be substantially correct, that is, if they were produced by the contraction of a heated outward crust upon a cold and therefore non-contracting interior, the result of such a condition might be shown experimentally. Several baked clay balls might be formed to serve as cores, say of 8 to 10 inches in diameter. These being fixed within molds of, say, half an inch to an inch greater diameter, the outer layer would be formed by pouring some suitably heated liquid material and releasing it from the mold as soon as consolidation occurs, so that it may cool rapidly from the outside. Some kinds of impure glass, or the brittle metals bismuth or antimony or alloys of these might be used in order to see what form the resulting fractures would take. It would be well to have several duplicates of each ball, and as soon as tension through contraction manifests itself, to try the effect of firing very small charges of small shot to ascertain whether such impacts would start radiating fractures. When taken from the molds, the ball should be suspended in a slight current of air and kept rotating to reproduce the planetary condition as nearly as possible. The exact size and material of the cores, the thickness of the heated outer crust, and the material best suited to show fracture by contraction, and the details of the treatment might be modified in various ways as to suggest the results first obtained. Such a series of experiments would probably throw further light upon the physical conditions which have produced the gigantic system of fissures or canals we see upon the surface of Mars, though it would not, of course, prove that such conditions actually existed there. In such a speculative matter, we can only be guided by probabilities based upon whatever evidence is available. This concludes Chapter 7.